Agradecemos a la maestra Juliana Chala, al ingeniero Luis Alberto Rodríguez, al ingeniero Mario Pérez, a la doctora Inés Sáenz por su participación y reflexiones acerca de las estrategias y acciones hacia una manufactura sostenible. Soy la doctora Dorailiana Medina, líder de la Unidad de Investigación de Desarrollo Acelerado de Materiales del Institute of Advanced Materials for a Sustainable Manufacturing en la Ciudad de México. La unidad se encarga del diseño, síntesis, caracterización y desarrollo de materiales innovadores biobasados y poliméricos para empaques de alimentos sustentables. Estos nuevos materiales deben poseer características amigables con el ambiente, es decir, un carácter biodegradable y compostable, que reduzcan considerablemente el efecto contaminante en el ambiente. Es bien sabido que los plásticos derivados del petróleo de un solo uso son un problema ambiental muy grande actualmente, por lo cual la unidad busca el uso de películas poliméricas biomodificadas usando polímeros ya existentes en el mercado, pero adicionando un agente biobasado como los residuos de algunos procesos agroindustriales, que disminuyen considerablemente el tiempo de vida del producto en el ambiente. La formulación y creación de empaques deben cumplir que sean químicamente inactivos, fisiológicamente inertes y altamente biodegradables, compostables, con propiedades de barrera adecuada para evitar el daño a los alimentos por agentes externos, sin alterar el valor nutritivo de los alimentos para el consumidor. Nos inspira a transformar la industria de alimentos. La siguiente conferencia, titulada Future of Advanced Materials to Achieve Sustainability, está a cargo del Dr. Vladimir Bulovic, director de MIT.nano en MIT. The floor is yours.
Thank you. Well, thank you very much. Oops, just a second. Try again. Thank you very, very much. It's truly an honor to have a chance to participate in this absolutely fantastic event. I can't tell you about how pleased I am to see the evolution of our relationship, MIT and Tec de Monterrey, over the 7 years that we have known each other really, really well. And it is amazing to see the opportunities we had to work on together. MIT does better work because we know Monterrey Tech. Our researchers publish better papers when we jointly publish papers. And as a result, we see the absolute opportunity of using what we've done up till now just as a seed of many more things that should come. My goal for today is to give you perspectives on how to translate basic academic discoveries into industries, into technologies that can grow and meet the needs of many. One thing that is often not perfectly understood is that we can invent many, many great ideas, but they're not really practical until a million people are able to hold them in their hands. So the journey of the discovery, from the discovery to a million people using the discovery, is a journey that takes at least 10 years. It's never been done in any shorter time. And so what academics are really good at is imagining what the world is going to look like 5 and 10 years from now. That is where we need a perfect partnership with industry, patience, as well as a transition from our labs into spaces that can take those very nascent ideas and grow them into the very small startups that eventually become dominant industries of the era. In many ways, we look at ways of translating those ideas by starting to work with those startups. And the best people to run those startups are indeed the students, the postdocs who invented the technology. They're young entrepreneurs who need nurturing support, guidance, and recognition by the existing industry that these are the key individuals to change the existing industries into becoming even bigger, even more important, even more powerful. So my goal for this next 25 minutes or so will be to give you a very quick journey through a series of opportunities that I think align extremely well with what this incredible new institute you're launching here at Tec de Monterrey is attempting to do. So first of all, congratulations on launching the Institute for Advanced Materials and Sustainable Manufacturing. The focus that you have chosen is indeed foci that will change the planet as we know it. You can find this on the website of the Institute. And there are plenty of new ones I imagine the Institute will embrace as it recognizes its strength, the strengths of its people, and the ability to reach out beyond the bounds of the Tec de Monterrey by connections with MIT and other institutions, other industries, and hence using your talents to solve those next set of really big issues, really big challenges that the world needs solving. I will give you a few examples of what my colleagues have done up till now, and some of them will sound silly as I start them, but only to get us into the technology. So here's one that is particularly intriguing. It's a technology for avoiding stiction on a surface. If you can understand nanotechnology really, really well, you can understand how to coat the surface with an extremely thin layer of molecules and will cause the stiction of the surface to change. This could be, you can think, very important if you're looking at air conditioning systems that you would like to more efficiently transfer the heat or the cold from the cooling unit to the environment around you. It also is really important if you have issues with your ketchup. If you would like to take the last ounce of ketchup out of your ketchup bottle, this is a typical experience you might be in. But if you ask Liquiglide to perfect your ketchup bottle, you will find that every single last drop, every single last gram of ketchup will nicely slide out of that bottle. The nanoscale coating for the benefit of our culinary experience. I will also highlight maybe the following. This is another technology that very same company developed. And the company was started by the laboratory of Professor Kripa Varanasi, an extraordinary mechanical engineer who used to work at General Electric prior to joining MIT and hence recognized the needs of technical growth and the needs of what does it take to actually take a brand new idea and making it technology everyone can use. Toothpaste now can be sold and actually is being sold by Colgate that allows you to actually squeeze out that last little drop of toothpaste out of the bottle. Again, not the technology that will be transformational necessarily in a way that would impact large efforts of squeezing the ketchup or squeezing the toothpaste. But it turns out this very same technology can improve the efficiency of steam turbines in power plants by 10 to 15%, as you reduce the friction between water molecules and the blades of the turbine itself. Or, as Kripa looks towards the next set of ideas, he realized that one big challenge that we utilize, that we have issues here, when we grow crops, the pesticides we use are enormous, the amount of pesticides we use. And if you can use the same stiction control to change the amount of pesticides that will stay on your plant, you should be able to dramatically reduce the amount of pesticides in the environment, hence making a much cleaner place. Indeed, it's estimated there are about 200,000 deaths per year from pesticide pollution. And it's because of this. The plants are designed to let, the leaves of the plants are designed to let the water go so it can slide down the stem and reach the roots, consequently watering the plant. However, this is the method we are using to deliver the pesticides to those plants. Well, if we spray about 50 times the amount that sticks to the crops due to the water repellency of plants. 49 times that what is useful is just being there to pollute the earth. Company AG Zen came up with a solution to change the conventional spraying, that is how the droplets bounce off, to this. Their droplets stay on the surface thanks to the treatment that they're utilizing. And so a conventional spraying that might deliver water droplets like you see right there on the leaves would become something like this, the pooling of water on the leaves to prevent the pesticides. Controlling the nanoscale, controlling that last layer of molecules, and hence the stiction, can have a dramatic impact on the agriculture if this particular technology is utilized. There is a demonstration at this point of about 10 times reduction in spray volume in the laboratories. Another way to improve our vegetables and fruits experience and use is indeed to be able to detect the presence of ethylene. Ethylene is a hormone, plant hormone, a molecule about nanoscale in size, about 0.13 nanometers in dimensions, that is emitted any times bananas turn from green to yellow or apples turn from green to red. Ethylene is a messenger between the plants. They simply tell to each other, oh, it's time to ripen the fruits. You know that if you have bananas that are green, you might be told that put it in a paper bag and they'll quickly become yellow. Why? Because the paper bag is made of material, wood material, pulp, that emits ethylene. And that ethylene tells the banana, you better turn different color, ripen. This is great as a communication between the plants, but it also is a challenge when you pick up all the apples from the tree and you leave them in a warehouse in a box waiting to be sold. If you leave that box in the back of the warehouse and one of the apples starts emitting more ethylene because it's ripening, it's turning kind of rotten, it will make the entire box turn rotten. If I can smell ethylene, I can tell you that box is ready to be sold. By detecting ethylene, I can change about 15% of the produce, vegetables and fruits, in the United States. And all you need to do now, thanks to this other company, C2 Sense, developed by chemist Professor Tim Swager at MIT, is to use carbon nanotubes. Those are those dark areas between the gold electrodes. By the way, those are painted carbon nanotubes between evaporated gold electrodes to generate a conductive medium that is sensitive to ethylene. By dressing those nanotubes with the molecules, 1 nanometer in length, that are sensitive to ethylene, when the ethylene comes by and binds to them, they will change the conductance, and consequently, you know, ethylene is in the air because the resistance from top to the bottom electrode will change. This, by the way, is a sheet of paper on which you paint the whole thing. The whole device weighs less than a gram and indeed is extremely inexpensive to make. Transformative technology that is reaching millions is being used, as I understand, in orchards in Brazil right now to prevent spoilage of the fruits being generated. Indeed, your center as well is looking at ways of preventing the spoilage of the food. And Professor Marelli in the civil and environmental engineering at MIT recognized by accident that silk has a really unique properties in preventing the spoilage. The story goes that there was a party at one of his research groups before he was a graduate student, and he was working on silk protein. So he decided to dip some of the strawberries in the silk protein and bring them to the party. Well, not every strawberry was eaten, and a week later he was looking at the strawberries, realizing there are some rotten ones, and then there are some perfectly fresh-looking ones. Those are the ones that he dipped in the silk protein. Silk protein is a perfect repellent, naturally derived, perfect repellent for bacteria. It seems to also prevent dehydration. It also seems to prevent moisture change inside the fruit itself. A banana wrapped in silk fibron coating has a lot less decay after 9 days of sitting on the shelf. As a matter of fact, if you put a 200-gram weight on the one that wasn't coated versus the one that was coated, you will see a significant difference in their firmness. You can similarly spray, this is vegetable noodles. The ones on the left started going bad. The ones on the right look as good as when they were purchased. This is an edible way to prevent food spoilage by deriving out of a naturally available material. Indeed, if you take the protein and you spray it in a particular way, you can encapsulate it in it, for example, vitamin C. You might be able to use it as a replacement to microplastics that we right now are concerned about as they are propagating through many of the technological advancements we are indeed trying to give to the world. This is one way to maybe make a natural way to generate such. Again, a very simple idea. And a startup company, indeed, that is developing it, Mori, is making tremendous strides in engaging the next and the next set of industries that could benefit from this great idea. If you are going to use different ways of processing today's materials, petroleum, right, is one of those materials that we know a lot about. It's being used worldwide. It's one of the most used material sets. It can be also used to make 10-micron fibers, if you follow material science professor's work of Jeffrey Grossman, that recognize that by extrusion of these very same material, you might be able to make, well, materials out of which to build cars. Cars that are lighter and yet as strong as aluminum in being able to deliver the performance one would need. Could we make cars out of petroleum residue as a way of generating the next steps of opportunities, of reutilizing materials in an environmentally benign way to indeed impact a significant challenge of our time? If you understand chemistry, like chemical engineering professor Michael Strano, you would also be fascinated by using such materials and cross-polymerizing them in order to be able to generate very, very strong material sets. Indeed, lightweight material that is stronger than steel as a result of a feat that was thought to be impossible, which is polymerizing a material in 2 dimensions at the same time. That has not been previously effectively achieved until his recent work. But the result is that he can make a material that is indeed extremely strong, and because it's using carbon-based structures, extremely, extremely light. Recycling of such material better also be possible. And so Professor Jeremiah Johnson in chemistry recognized that one great opportunity, as we do recycle plastics, is to introduce triggers inside those plastics. Triggers that would allow them, if needed to be recycled much more easily with a much smaller energy budget. So utilizing, again, very simple nanoscale additives to the conventional plastic making, those plastics would be ready-made. They would not be suffering in their mechanical properties, their physical properties, but when you need to recycle them, they will be ready to be recycled in a much more efficient fashion. These are examples of using matter, using materials in ways one could not even think of before, because we finally have a way of controlling the nanoscale, understanding what to do with it and how to put it together almost like Lego blocks that allow us to then rethink what the possible technological implications can be. Anything we invent today, I like to say, anything we invent today, a year from now, will be old news. What that really means is that those of you today who are students thinking about, well, everything will be invented by the time I reach the place where I need to invent new ideas, untrue. There are so many things to be done. There's an infinite number of things you need to invent. Keep training and practicing, keep immersing yourself, and you'll find yourself, once you have enough knowledge and enough dare to try, you will find yourself inventing that next great idea. No question. Just dare. And follow your leads, follow your professors, follow the best students you see in your class, and say, I can learn from you. Notice, as I talk to you about various inventions here, I have mentioned professors from many different departments of MIT. The one strength of MIT as a campus is that all the buildings of the campus are connected And there is not a sense that here is where the electrical engineering stops and here is where physics starts. No, because the world of tomorrow is about interdisciplinary interactions. And I applaud you for launching an institute that is thinking of it exactly that way, looking at ways of linking the disciplines that have not necessarily before found themselves connected quite as seamlessly. That is where the new inventions lie, at the cusps of disciplines, places where the conversation between a medical doctor and an engineer can lead to an entirely new life-saving engineering technology that the medical doctor can apply. These are the opportunities of tomorrow, linking the fields and rethinking what they can be. Our colleagues in mechanical engineering think about how to put the world together from scratch. And of course, 3D printers have enabled us to do so. They've recently launched, among many MIT 3D printing startups, this is a really big one. It's a really big one because they make really big things using very strong materials like metals that you can directly 3D print. Started by mechanical engineering professor John Hart and his colleagues. There was even recently a New York Times article about them because indeed it's impactful. This is a way that the world will change. They're a young company. They're only maybe 3 or 4 years old. Their real impact that will reach millions and millions will happen in another 3 to 4 years from now. That's what I would expect based on the trajectory they're following. And based on the fact that they believe in what they do. The strongest advocate for a technology is the inventor of the technology, not a company that will take it from you. Because when they take it from you, it's someone else's thing that they took, not their own. What you as an inventor, you as a creator of the idea really understand is the potential of it. And that's what we see the startups do. Often the startups don't get paid very much. You know, if you work long hours, but you believe in what you do, knowing that you will get to a place where this will impact the world, and hence all your hard work will be transformational for millions that follow. One of the examples of what can you print with such a 3D printer, this is a different version of it, also from John Hart's lab, is material that uses biologically derived materials, wood, cellulose, and can print it to make it tough as a bone and hard as aluminum, while also plant-derived. This is a tooth printed in that fashion. You 3D scan the mouth, you figure out what the shape of the tooth you need, and you just ask your 3D printer to print it for you, and then you implant the tooth so that the patient has that extra tooth that's missing. You can do very complex structures using 3D printing as well. And Professor Portela, also in mechanical engineering, studies the ways to make the lightest materials that are the strongest to impact. If you want to make a bulletproof vest, this might be one way to do it. As it's thin, light, and extremely strong, stronger than typical other materials you might want to wear at that weight point. The trick is in understanding the mechanical properties of matter and using those mechanical understandings to design the 3D structures that will be able to imbibe collect the energy of the impact and spread it among many lattice sites, consequently not breaking any single one of them. If you understand that, and you realize that the forming of matter from scratch, maybe through 3D printing, could change the way we think about what the next set of materials we use might be, well, you can also realize that we can recycle the plastics of today, like plastic bags, and make fibers out of them. And not just any fibers, but actually fibers that breathe, that keep the person wearing the shirt made of that fiber cooler. Of course, that might matter when the climate gets hotter. And it is indeed recycling matter that we have indeed right now have available to us. You are extruding fibers, for example, to form those fabrics. But you don't have to just extrude regular fibers. You might be able to extrude fibers that use unusual materials, chalcogenides or metal oxides, that happen to be extruded in a concentric fashion, making a hollow middle. This was an idea 2 decades ago by Professor Joel Fink in material science. He now electrical engineering as well. He wanted to figure out a way to use total internal reflection. If you remember, when the light goes off of another matter at a very glancing incidence, it will bounce off of it. He realized he might be able to use the trick of total internal reflection in a hollow fiber to guide carbon dioxide light. Carbon dioxide lasers are used typically to cut anything. They are infrared lasers that are exactly matched to the vibration modes of matter, and consequently, when they get absorbed, they cause the fissure of the bonds and cut anything. Well, he wants to guide them through a fiber without cutting the fiber. Why? Because if I could do that, I might make the best surgical scalpel ever invented. He succeeded, and this fiber can guide CO2 light. Why is this the best surgical scalpel? Well, I told you CO2 light can cut anything, including skin. And if it cuts skin, you can choose how deeply you want to cut by choosing the intensity of the laser. That's cool, but that's not the most important part of it. The most important part of it is that when the carbon dioxide laser cuts the skin and opens up the wound, you would expect you will start bleeding, right? Because your skin was just cut. Not with this laser. The heat of the carbon dioxide will cause, on the spot, coagulation of blood. So you can make an incision and avoid the bleeding that is typical of that. Now you might be able to do operations that could never be done before, like remove a tumor from a lung of a patient without flooding their lung with blood. These are solutions that enable hundreds of thousands of operations to be performed using this very straightforward idea: guide light through total internal reflection by extruding a fiber. That is all the technology is, and can transform industries as we know it. OmniGuide Surgical, indeed, is providing tool sets for this type of idea. These very same fibers, I told you, can guide any color of light. They can guide infrared, but other colors are as well possible. So allow me to show you a video, and this one has a mouse in it. I'm going to show you, so I'm just warning you, those of you who don't like mice being subjected to experiments, turn away for a minute, Those of you who don't mind it, I'll just show you, because it is a transformational way of thinking about spinal surgery. This very same fiber, if in hands of Professor Polina Nikeva, also from material science, but also the one who works with the bioengineering teams to understand how to do optogenetics, would allow her to actually optimize the fiber for blue light, connect the fiber into the spine of a mouse that was paralyzed, and make the legs of the mouse move by shining light. So here is that mouse, that's the back of the mouse, and up on the top you will see in a moment flashes of blue light. Those flashes of blue light will coincide with the moments that the mouse moves its leg. It is the light that is triggering the neuron to send the signal to the muscle to indeed move the muscle. Is this a cure for paralysis? Not quite yet. There's a lot more that needs to be done to make this real. But it certainly opens up venues and thinkings, again, through a very simple idea: make the fiber and have the insights into how can that light interact with the human body in order to be able to generate, indeed, solutions for paralysis in this case. If you have a way to extrude a fiber, make the world's longest flexible fiber battery. Professor Joel Fink, the same one who made the OmniGuide fibers, now is making, in the same format, flexible batteries that you can wrap around any object and provide capacity at will, depending on what's the length of the fiber you happen to use. This one is wrapped around a portable submarine, like a submarine drone. Seeing the nanoscale allows us to see that world that then opens up our eyes to the next set of possibilities. What you're looking there on the right is a video of atoms. Every one of those circles is an atom. We can now, for the very first time, over the last maybe 5-10 years of available instrumentation, for the first time actually see videos of how the world truly looks down on the nanoscale. It is those insights that now open up our eyes to saying, before I could only imagine what really happens down there. Now I can see it. And we like to say the picture's worth 1,000 words, or maybe in this case 1,000,000 words. because it allows you to understand what you couldn't have imagined as easily. The complexities of the fissure opening in the lattice, the complexities of the atoms adding themselves. This is a 2D sheet of material, tungsten diselenide. You're looking at tungsten atoms bouncing around. The only reason why they don't bounce out of the picture is because they are sandwiched between two other sheets of material of boron nitride that prevents them from running away. This is a tool at MIT.nano, a tool that now allows us to see to the scale. You can see the scale bar of atomic scale, sub-nanometer. Now, those kinds of materials now can allow us to reimagine quantum computing. We made, thanks to the recent work, this is Professor Will Oliver's in electrical engineering, came up with ways of utilizing such 2D materials to make little energy storage units, the smallest necessary capacitors for superconducting qubits, allowing us hence to miniaturize the qubit and maybe actually usher a true age of quantum computing that we believe is truly upon us. There are many examples to show you, and I showed you a lot of the small ones. Let me show you a big one that might make a difference. This is from Kripa Varanasi's work, a company they launched called Infinite Cooling to disrupt the way the power plants use water, because water is scarce. You saw that big plume of water steam coming out of the chimney of a power plant. There's economic costs. There's a plume formation that some people don't like as aesthetics, or maybe it carries additional particles in the air. So a solution is to follow Kripa's group. Here's a steam from a beaker, and this grid, when turned on, will attract all of that steam and indeed collect it, filling that beaker with condensate water. If you have a typical coal-burning power plant that supplies the village, that same coal-burning power plant can supply many of the houses in that village with water. The steam burned off. It's already semi-purified in a process. This has a tremendous impact opportunity when it comes to water collection as well as pollution as we know it. And all it is a simple technology. Again, you need a nanoscale coating over a grid of some sorts, but very scalable. We've actually tested it at MIT. Our power plant in a nuclear research lab installed it. It works really well. And there are examples and examples of additional ideas that indeed they're trying to deploy. My time is nearly at end, so allow me just to show you a couple of more, one more idea. And this is a solar idea, another scalable technology. One of the efforts of your institute indeed is lightweight materials. And I'm a true believer that that is indeed a very right way to go. We interact with surfaces of matter, and surface is all I need to make a really good solar cell, a really good LED, a really good sensor, a really good haptic responder. So coming up with lightweight format would go a long, long way. So we started it by making solar cells on, in this case, on paper. And does it work? Yes, it does. This is that piece of paper painted with some organic dyes. Shine light on it, and you'll have enough electricity to run a little electronic device. But it is a piece of paper, and you can treat it and use it like no other solar cell you would ever think of using, which is indeed to be able to feed it through a printer, if that's what you wish. Print on top of it, let's see if it still works. Shine light on it, it still works. This is a different way of thinking what a solar cell can be and how it will be deployed. And it matters to me, but it really matters to nearly 1 billion people around the world without access to grid electricity. This is the way they get their solar energy. They need to carry it for about 10, 15 kilometers into their village. This individual, I bet, doesn't care what is the efficiency of the solar cell. I think the only thing they care about is how many trips they need to make. Give me a cell that weighs 100 times less and is half as efficient, and that's 50 times more power on my back in one trip. So watts per kilogram, I think, might be the metric that it could be truly transformational, especially for the developing world as it tries to power itself. And so we wanted to test it. We indeed partnered with a company, this is a company, a young man in yellow shirt. It's known Karma Solar. It's on the east side of India. And we have bought for him an expensive but presently available version of a flexible solar cell. This is not our technology, this is someone else's, and it's heavier than what we imagined we would make. He started an agro-business, irrigation business. that is typically done by utilizing diesel pumps. Now he can do it by utilizing solar installations. A simple one that is actually already changing lives. He is finding himself indeed busy with his business, and he doesn't have to have 4 people carrying heavy panels that will crack. It's him deploying this on the back of his bicycle. Transformational from the way of being able to deliver the next set of ideas. So I will conclude by one more time congratulating you on the vision, the inspiration, and the opportunity that you will give to the generations of students that will follow in this institute. You're bound to invent new horizons that no one has yet seen today. And know it all along, if you ever need us to help, if you ever need us to step, we would tremendously be thankful to have a chance to indeed work with you and continue working with you. Thank you very much for having me here. Really appreciate it.